Let's try now.
Is it better now? 1, 2.
Yes, let's say yes.
It's
Perfect.
better. It goes. Okay. So here it's the Vlasov equation. It lives in the old space or in a bounded dome or in a periodic box, because that will be the simplest thing, basic first thing to consider. The point is that there is the electric field, which is computed in terms of the total charge, and the total charge are the ion, the electron minus the ion, and this guy is constant. So you inverse the Laplacian and take the gradient, and you get the AOF. This is a standard simple, and it has two good properties. First, that the total density is constant, and the second, that if you just multiply by v squared over 2, integrate by part the number of things which will be convenient, you get that you have a natural physical quantity which is conserved. It's the density, it's the kinetic energy, because you have the v squared, and the electromagnetic energy, which are the E squared. So these two are conserved. Okay, now,
The technology is playing up.
oh, I should use this. Do you want me to use
No,
this
I think
one?
it works now.
I can try again. Okay. Yeah, it's okay. Now, more or less, the goal of my talk, it will be to introduce what is called in physics the quasi-linear approximation. I consider the problem in a torus, which may be the first thing to do. A tokamak is not a flat torus, but make the first approach. So all takes place, the x variable in a box, that's t at the power d, and at some point d will become equal to 1. And the thing I do is I integrate with respect to x to look at the general profile of the density of particle. So if I integrate with respect to x, the variable v, the term v grad x, after integration with respect to x, disappear, and then the equation is equivalent to two equations. One is the total, the variation of the total profile dt of g, the same g which is here, and the other one will be the equation dt of, that will be an h here, the dt of h here instead of f, dt of h plus v grad xx plus a of h, because h is depends just on the difference, plus the gradient of v, g plus h. Now, when you have that, you integrate, you have then this equation, and you have this one. And if you integrate with respect to v, or you integrate with respect to v, you just get the second equation, dt of v plus grad of v, e of h, h. So that means that what comes out is the gradient with respect to v of a of h, h dv. Then I'm looking for an equation for this problem, which means finding an approximation of E of h, h in terms of the global profile. So this is the equation 1, and the equation 1 is typically a closure problem. Try to find an approximation of macroscopic quantity in terms of the discrete one. And this is what people in physics call the quasi-linear approximation. Okay, so far so good. Now, that's what I told. It's the what I want to do is to describe this thing. This could be compared and maybe with other type of ansatz where you define for kinetic equation, starting from kinetic equation, you define an equation for the average in space. So even from Boltzmann equation, you can do that. And you get equation for the homogeneous Boltzmann equation, the Balescu-Lenard, the Fokker-Planck-Landau equation. Let's say all these equations more or less have the form dt of f plus v grad x f equal q of ff. And the game is to integrate with respect to dx and try to, assuming that you get an equation plus the integral of equal the integral of q of h dv, and the problem is to study this quantity. Okay, and this is a justification of this type of equation. Now, in fact, when I started to work on this type of problem already many years ago, what was the homogeneous equation was considered in our community as an intermediate step to do a numerical computation. You make fractional you make fractional steps. First, you compute the advection dt plus v grad x, which is this first part, ignoring that. Then another part, you ignore the advection and you reiterate. That was very popular. But what's happened is that, in fact, this type of equation, globally integrated with respect to x, they do have their own interest beside the trick for numerical approximation. And in particular, the one I want to talk about is the quasi-linear equation. And I start to be interested in the subject after a seminar in Vienna with two people in physics, Pat Diamond and Shikoshin. And they were, I've just read the paper of Moore and Villani, and they came to us asking us, well, do you think that this would help to understand the quasi-linear approximation? And after that, I came with the answer that maybe slightly yes, maybe slightly no, which is the point I want to extend. Okay, so far so good. So the first thing that you find in the old book of physics, which runs under Qual and Triple Piece, or more recent, the Nicholson, is to use some type of Dunford calculus. They don't really give the name Dunford calculus, but it's more or less what they do. And I will do it for you. And this is to try to write the equation, and then first to look at the equation where taking g of t, g of t of v will be a slow profile. So it's natural to start by the study of the problem when g is independent of the time. If g is independent of the time, the equation becomes a linear evolution equation, which you can write dt of f plus e of small f grad v of g, for which e is still given in terms of f by this formula, and where the total density is equal to 0. Now you write that as a semigroup. It will be a group, but since I am considering for positive time, it achieves the semigroup aspect, so the exponential TA, where a of f is minus v grad xf minus E of f grad G. Obviously, this of A minus A is the generator of the semigroup. And the first thing that you observe is that if you look at the resultant of the semigroup contains exactly the imaginary arcs as a part of the continuous spectra. Now, beside the, okay, I should not move from one side to the other. Beside of the continuous spectra, you see we integrate with respect to V, inverse the Laplacian, take the gradient, you construct a compact perturbation. So what will be happen will be that for the positive time, here there will be eigenvalue, and this eigenvalue, they are of finite multiplicity. They are bounded here by a certain constant capital lambda. And if you bound here, there will be just a finite number of these eigenvalues. And they are simple. So then what you do, the last line you are here, you make some contour deformation. Oops, around that. Cut a distance delta arbitrarily small, lambda arbitrarily small, and you get the asymptotic formula, which is written here, which is a consequence of Dunford calculus. Okay, that's not, but that's the way, most convincing way to look at the problem. Okay, now the basic thing, or one of the basic things of my talk is that if I go back to the first equation, you see this quantity is conserved. So it cannot support a growth in time that will go forever. On the other hand, if I come back to the Dunford calculus, which is here, it supports, when T is fixed, eigenvalue of positive real part. Now it's for G fixed, for G independent of the time. Now evolving in the time, one would like to look at the instability which may come from this quantity. Okay? Which means in some sense there is a contradiction between the linear problem being unstable and the nonlinear having to be stable. That's the situation. Okay, so the first thing I want to do is a classical, and then I will do that in 1D. Many of the issue of this talk will turn out to be in 1D, but it's already a very important issue, which is in particular if you look at a beam, but it's also a way to understand the problem. So the first thing I want to do is to give a sufficient condition so that this guy will not be here. And the sufficient condition, it's already old. It's due to Kruskal and Gardner, and it goes that way. You can take even a more general potential, V of x minus y. It's not an issue, but then you make the hypothesis that G prime of V is equal to minus H of V, where H of V is just a positive function. Why does that mean? That means that if you look at the profile of G of V and T, assume that T is fixed now, it's something which is like that, which has a principal bump, but no secondary bump, which is an element of this story. Now, if you do that, you multiply the equation here by minus F by minus H by H minus H minus 1 of by H minus 1 of V. And if you do that, using the fact that G prime is H of V, you have a cancellation, and you get for the next slide something which I did. So you get for the next slide, you get d over dx of Vf, because these two terms they have cancelled. And when you integrate that, you recover Vf. Vf is the gradient of the evolution of the density. This is bounded by, it's equivalent by the derivation with respect to time of the density. So you obtain one slide more, the relation. So I just move back because this is the relation I want. You obtain this equation, and you see this is a potential which is positive. This is the kinetic energy. This will be the electric energy. Both are positive. The system is stable. Okay. Now, after that, I move. So then I will move further in the analysis of this eigenvalue whenever they exist. Okay. So since it's a problem which is done in 1D, and since the G is capital G is independent of X, I can integrate by Fourier. I can use a Fourier decomposition, writing the density as the sum of Fk exponential minus Ekx. And if I look at the resultant equation for the equation lambda A, lambda plus A of F equals G, I look at that in Fourier space, you end up with the first equation, which component by component is lambda minus EKV plus EK over K squared, gradient of G rho K equals GK of V, which is a standard equation. Then when you have done that, rho K is the Fourier component of the density, you integrate and you obtain 1 plus AK, the integral of the gradient of G over lambda minus EK dV. All that is factor of rho K, and this is equal to the right-hand side. The right-hand side is integral of Fourier component of the source, GK of A, equal lambda minus AKV. Now, it's clear that if you want to have an eigenvalue here, you don't want to have an eigenvalue. This has to be 0, not different from 0. And if this quantity is 0, you will have eigenvalue. So this expression, this is called d lambda k, is called the dispersion relation. It's very standard in wave problem. And before going further away, I can call this function the dispersion relation with will of k positive. This is, there will be an eigenvalue if and only if you have a d lambda k equals 0. Now, there are very simple computations, and G, capital G is real. If you have this quantity, which is 0, the conjugate lambda k with minus k is also a solution. And of course, as I put that on the board, lambda k given, the number of solutions of d lambda k is finite. This is just a version of the Cato theorem for semigroup of perturbation of the generator of a semigroup by a compact perturbation. And also, you have, and now, if you have an eigenvalue, then you can put that equals 0 on the right-hand side. If you have 0 in the right-hand side, you find out that any eigenvalue will be given by the formula K. A lambda K is 0. This is the electric field at the point 0, because I have I K that the gradient with respect to X over K squared. This applies to rho K that give A of lambda K of 0. and you have this term and its frequency. And so this will be the basic eigenvalue for this problem. This is classic in physics. Now, the next thing I would like to do, since it's explore, I will be happy to extend that to any region on where they have real part of lambda greater than -a, this resolution. And this is inspired more or less in the thesis of Pierre de Gon. It's also inspired a series of work in scattering theory. And I will show you on this example, it's very simple, how it can be done. The first observation is that I want to extend the resolvent. And to extend the resolvent, I will have to extend, if I just go back one slide, I will have to extend this and this to the negative real part of lambda. Now, there is a simple observation, which is that if I look at 1 over lambda minus at, this is the Fourier transform, the inverse Fourier transform of 1 over k exponential minus e minus lambda over k eta, and that works very well as long as the real part of lambda is positive. So then this scalar product, when the real part of lambda is positive, is the same thing as this one. Okay? Now, if I assume that the lambda has no more real part, this may become to 0, and I have a trouble in expanding the right-hand side. Many people do that using complex calculus and introducing the Plemier formula. I want to show it comes very easily. I want to kill this bad behavior, because if real lambda is positive, is negative, this will go exponentially with lambda, with eta. The only way to kill it is to suppose that the Fourier transform of G of eta is exponentially decreasing. And that by Palais-Wiener theorem, that means that G is an analytic function in a slab, which means that I complete this picture, which I will do right here. I complete the picture now at the pole. This, you have a function which is defined for real lambda positive. You use the fact that you want to extend that for a G that will decay exponentially in Fourier transform in eta. So it decays exponentially in eta. That means that as a function of V, it's analytic in a region from minus a. So that G and G chapeau of eta is something which decreases exponentially for eta going, modulus of eta going to infinity. Okay, and that's exactly the Palais-Wiener theorem, and I will use this space of analytic function in the rest of the talk. Okay, so far so good. Now, I look at the dispersion relation, that for the same reason, if capital G is an analytic function, I can realize the same extension, and the only thing that will remain for the resolution are the eigenvalue of the pole, the 0 of the dispersion relation in the left-hand side. Okay, and they are not eigenvalue. It's not the same. They are not the eigenvalue of minus the lab A, because they are obtained by extension over the extension in the left-hand side of the resolvent. If you will look at time going to minus infinity, you will extend the resolvent to the right-hand side. So then I have construct extension, provide everything is analytic in a strip. By the way, going back to works on the Landau damping, most of the previous paper were using some analyticity hypothesis. This is completely consistent with, it is fully consistent with what I say here, okay? So, and then you obtain exactly the same asymptotic expansion, except you don't have it in LP norm, but you have it as soon as you make the Fourier, the scalar product with a function which is analytic or can be extended in the same slope. In some sense, people can look in the old time used to call that ultra distribution to connect with other type of Fourier analysis. You can look at what's happened when you want to extend only for real part of lambda equals 0. For real part of lambda equals 0, you don't need the Fourier transform to be exponentially decreasing, the Fourier transform of the data to be exponentially decreasing. It's enough that they be continuous. So in some sense, it's the way you recover the fact that the extension up to real of lambda equals 0 is just a distribution in the classical sense that you can compute with Plemiel formula. So then I end up with this nice formula, which is valid for, say, for polynomial, Hermite polynomial, any analytic function that will do that. Okay? Man, no. And then what will be the quasi-linear approximation? Quasi-linear approximation that I announced is to write g of t f equals g of t plus h of t x v, and try to see what can I do if I just go back to my introductory slides. So if I go back to the introduction, I have now decoupled the system into these two equations, one for g of t and the second for the perturbation. Okay, now I move that. If I move that, I am not going to find a result that will be valid for any solution. I start to look for typical solution and try to generalize after that. The most typical natural solution will be to start with an eigenvalue of g of 0, okay? So something which will correspond to the eigenvalue of v grad xf plus e of h grad g of 0, say, e of f equals 0. Something equal lambda f, for instance, or minus lambda f. Okay? So if I start that, then I want to make this more precise, making the eigenvalue, the lambda, depending on the time. So to make the lambda depending, so then I will look at the same problem when instead of fixing lambda, I will assume that lambda depends on time. And to have lambda, so I call it lambda s, and I will assume that g of t moves slowly with time, and that lambda, and I take that lambda of t is a simple eigenvalue of the dispersion relation. So let's say lambda of t is an eigenvalue of the dispersion for g of t. Then I consider A of h as the gradient of the density of h, the gradient with respect to h of g of t of v. And now the difference is that g depends on t. There is a gradient at the hypertext d of h. And for d of h, which will be like a diffusion, I assume that formula d of h is 1 over pi, the integral of 0k, the modulus of the vector k square, the real part of exponential lambda s, exponential 2 integral from 0t, the lambda s ds, over k time lambda s scalar v minus the imaginary part of lambda s square plus the real part of lambda s square, which is a formula that will come immediately from, will be justified by the use that I make of it, and that will be a theorem. I assume that g of v at time 0 as that the dispersion for the equation for g of v, I should write it down here, dispersion of the dispersion relation for g of z 0 lambda 0k as a smooth simple root, as a simple root. Then I will assume, in fact, that for some small time, there exists a unique solution of the equation, g of 0v equals g0v, and dt of h equal minus Laplacian of h gradient of v, and where h here is given by ak0 gradient of v lambda minus k exponential lambda k minus ek. And I keep the hypothesis that lambda t is a simple root of this equation. Okay, so then move on, and what I will prove first is the theorem is, if I go back to the theorem is that if I have simpler root equation, then I have an equation of this type where h of k is given by 8 by d gradient of v over lambda k plus lambda a minus k, lambda k being a simple root. Okay, with that on, I move and I compute d. I make that by iteration, and I compute the d of hn. I use the fact that if k and lambda k are solution of dispersion relation, the same is true for the conjugate of lambda and minus k, combine the two terms, and I obtain a coefficient which is positive, which is lambda s exponential 2, the real part from 0f, the lambda n ds, minus lambda n of s minus v, the imaginary part of lambda s, plus the real part of lambda s squared. And with that, as long as this is positive, I can solve this equation because there's a gradient with respect to v, a gradient with respect to v, and then I have a parabolic equation. And with the analyticity, solving that for short time, assume everything has to be analytic in this story. The time, the lambda depends nicely on S, and so for short time, the positives of this quantity is preserved and can make by iteration and prove at the end of the day the existence of a solution of G of Gn plus 1, gradient of V of T of G, gradient of D Gn plus 1. Now, what I have done with that, is the following thing that I have done with that is the following observation, which should be somewhere. Where did I make? Yeah. Then, when it is done, I will do the same thing by rescaling the perturbation. Rescaling the perturbation means changing G of V by G of T plus epsilon H of epsilon. But the introduction of G was a quadratic operation that makes appear an epsilon square in the equation 15. And as a consequence, you see that as long as I have a solution, dt of G epsilon is bounded by epsilon squared C. Now, if I want to make this ansatz in the full equation, it is here, you see that if lambda will be an eigenvalue for G, the dt of lambda, that the dt will be just the derivative, the derivative of T lambda, so that will make the lambda appear, plus this term, plus the grad of G, that will be an exact eigenvalue. So the difference here involves the derivative with respect to time of the gradient of G of the slowly varying profile and of the lambda of T, which now depends on time. So I can write this equation with a reminder, and the reminder is d of tv that multiply the derivative with respect to time of G, which means that it's a C of T of V dt of V. Now, if I started from here as something which is of the order epsilon square, that will tell me that here I will have epsilon square, another epsilon square that will appear in the remainder. So that's the way I can turn the crank, and I insert G epsilon plus epsilon HS in the Vlasov equation. Observe that I get EF where epsilon is the gradient of the Laplacian -1 of F epsilon minus F epsilon. Turn the crank, and I just observe that instead of having an epsilon square, I have increased the error by an epsilon order of epsilon 3. So in some sense, I gain one degree of approximation in epsilon of in the approximation of the equation. Okay, so I turn that, and then I come back and comment on that. The essential hypothesis is that the profile G of 0 will be analytic, and that for some k and lambda 0, G's lambda 0 and k become a simple root of the diffusion equation. Now, that says the following thing, which is written in this theorem, where I have combined the positive, the lambda k, and the conjugate of lambda minus k as the following formula. I call h of t of v equals this formula, which gives the perturbation, d of h of epsilon equals this equation, and the observation is that this construction provide an approximation of the order epsilon 3 of the profile instead of the epsilon square, which was here. Having done that, I can turn the crank, and turn the crank. I can reiterate this process and show that I can obtain an approximation of any order in epsilon. What is the price to pay is that all that is done for short time with analyticity hypothesis, which means that in next step, I reduce the domain of analyticity of the validity for the formula. But that's the formula. Then I can reiterate that. The first thing to reiterate is just to comment what I have done. What I have done besides this extension computation can be expressed in the following thing. You have a dynamic, which is the dynamic of the Vlasov Poisson equation. This is a dynamic we will not go to infinity because you have conservation of energy. But at each step, you try to replace this dynamic by the for small time, the dynamic computed with the tangent derivative to the flux. And this tangent derivative can be an increasing or decreasing mode. What I have shown here, that I can do, when I do this type of thing, I can construct an approximation of order epsilon square and higher order. Now this could be called the tangent dynamic, and this type of idea have already appeared once in a paper of Bobilev, Pulvirenti, and Safiro. What they have done, they have not looked at all the time here. I have just considered the problem at the time t equals 0 and try to construct an approximation of the profile. And doing so, they get an equation which is exactly the Balescu-Lennart equation. What has to consider here is that there is another way of getting the Balescu-Lennart approximation, which was considered by Lorcin-Raymond and De Hering. What they do, they start at time 0, where they have a classical dynamic, but with a system of interacting particles and the Newtonian dynamic and some randomness. And they prove that in some regime, what I proved here, what I shown here, is valid when you start, is valid for a small time with a slight modification of the equation. Okay, now I move on with some other comment. Okay, now the other thing which, if I compare to the physics, first, this computation that I have explained to you was based on an asymptotic description along the dynamic of one eigenvalue, which I call monomode. Let's say one eigenvalue with a real part, with an imaginary part, and its conjugate on the other part, but they are both simple. Now, the other thing which happened is that the multiplicity of the eigenvalue may increase with time, and in particular, you have the interaction of the two modes. And it's conjugate with another property, which I can describe once again here. You have this equation. Now it's less mathematic, more sentimental. you have the gradient of V, of D, of G, of the gradient of G, and V gradient of G equals 0, you see that as long you have eigenvalue, you have started from a profile which has a bump, because otherwise, with the theorem of Kruskal and Kruskal-Gardner, there will be no eigenvalue. Now, since you look at this equation, it conserves the mass, but it introduces the d of gradient of G, V, gradient of G square dv dt. This is bounded. So that means if this quantity is bounded, but in the meantime, with that if this profile, that will have the effect of flattening the profile. But then, if you flatten the profile, the first eigenvalue, if you flatten the profile, the first eigenvalue will go to zero here, and this term will become a degenerate coefficient because it did introduce the real part of the smallest eigenvalue. So you have a double effect, which means that the eigenvalue may migrate to the imaginary axis, and in the same time, this may combine the amount of interaction. Now, combining these two types of hypotheses is something that you find in books of physics, which are not completely mathematized, which people give the name of wave-particle or wave-wave interaction, which correspond to increasing the connection of the eigenvalue. Okay, I come back. So I come back to this consideration. The other thing is that all what I tried to do, you see, was to describe how the eigenvalue of the linear of the problems, the eigenvalue which are of the linearized problem at zero will give instability that will live in this region. Now, since you have global conservation of energy, this quantity are supposed to go to zero. So it's natural to consider a problem where you have no singularity, no eigenvalues. And this is exactly the hypothesis which was done in the paper of Moore and Villani. And in this case, you show simply that the electric field, that's their contribution, goes to zero, which means that in the total balance of energy, you have transfer of energy from the electric field to the kinetic energy. And that's the case where you have no eigenvalue. Now, and this proof, so if you have no eigenvalue, this proof can be simplified with some use of the Dunford calculus, and it is in the spirit of the paper of Grenier, Nguyen, Rodyansky. There are a certain number of things which can be simplified. Now, of course, what people would like to see is what's happened between this regime for large, which is okay for large time, and this regime where I tell you in a sketch of proof that it is for short time, and I have been very careful not to tell you exactly what I mean by short time. Now, the challenge is to move from this picture to this one. And of course, the point to study, the next step is to see what's happened when you start from a situation where you have an eigenvalue, say even a real at zero. Zero is an eigenvalue of the zero of the dispersion relation. The rest of the spectra is there. And in such situation, the move Villani doesn't work. There is no reason why E of TRFX go to zero. It will remain bounded. But if you have two eigenvalues, let's say here and there, it will start to oscillate and give some perturbative, strange perturbative regime that people observe in plasma. And that will be, in fact, if you look at the book of physics, this is what people in physics call the Landau damping. Not the one which was difficult for us to give complete proof, but the one where you have eigenvalue here. And the last step will be when you use the profile equation, which indicate that the eigenvalue will go to zero, what happened at the transition for an eigenvalue coming from there. So that's what I wanted to tell you.
So thank you very much. So any questions for the speaker, either from our live or online audience?
Can you expand a bit what you meant by short time there?
I told you that the point that I did reside in the node, and that's in this phase, the thing which is the weakness of the and it remains to do. Okay, it remains to do also in the, for instance, if you look at the paper of De Hering and Saint-Raymond, was approved a very short time, which in terms of the number of particles, in terms of the fact that they are not, that it's a weak coupling. And then they say that they have a time, but they say it's not enough to get the conclusion to transfer from one to the other. Okay.
So I wanted to ask about, so you mentioned here the Penrose Criterion. The Penrose, what's the difference between no, I know what Penrose is, but the difference between Penrose and
what is, I skipped that, but it's something I look at the problem in 1D. So if I just rewrite that, I can tell you in if I move back to the dispersion relation. Here you see, this is the dispersion relation, okay? So you want to see if it is zero or if it has a zero or not. And the construction of Penrose goes that way. You take lambda real, okay? So you take lambda belonging to R. And you consider the curve, which is spanned by this term in the complex domain, which will go by the attack when lambda goes to minus infinity 0, when lambda goes to plus infinity 0, for instance. And then the Penrose criteria is to say whether or not one will be in the image of this curve, because that will be a point of the image. And this is, if you analyze more carefully, this is completely equivalent to say that you have bump in the profile.
Right. So
now,
So, because you mentioned the Gardner-Kruskal, so what's the difference between the Gardner-Kruskal, between and
the opposite.
okay.
Gardner-Kruskal say nova. Okay, now there is a limit case, which will be something like that. This will not fit in Penrose. No, this will not fit in Kruskal because here h prime of v is equal to 0. This doesn't fit either in Moore-Villani because it's obviously not analytic. And on top of that, with this situation, once again, for physics, you have approximation which are on the imaginary axis. And moving this value to the imaginary axis is another story. Now, the last game you can play is to try to put some randomness on the distribution of the eigenvalue at time 0 and try to see if this randomness propagates. If the randomness propagates, if you have a propagate, and if E becomes a random variable with a good property of decorrelation, then all what I have written here is simpler, and it's an adaptation of paper of Vlasov and Poupeau and people of this generation. Now, looking at the propagation of chaos is something which is much more difficult for this problem. More or less, it is present in the contribution of Lord Saint-Raymond and During at some point, without getting all the result. But once again, if you look at literature of physics, they involve the idea that it's like weak turbulence, and it is what say weak turbulence, and that should work. But that's once again needs slightly more mathematics than what there is on the table now.
So any more questions? If not, let's thank the speaker again. Thank you very much. So see you all on Monday for our regular analysis seminar online, and on Thursday in person for the special session. So bye.